Well, I'm going to go ahead and get started. So hopefully the rest of them looks like Luke's coming in now. Hopefully Melody and Hannah will find their way in soon. I believe this is recording. I can't swear to it. Yeah, it is. Okay. So we're going to go ahead and get started. So yesterday we left off talking about how to interpret the partial derivatives. So we want to get more into that today. And then at the end of class, we'll probably have time to start tangent planes and linear approximations. Probably won't get to linear approximations, but we'll start tangent planes. So I'm going to share my screen with you so you see what I'm seeing. It's a little more clear, right? I'm just going to show myself. Okay. So basically, yesterday we talked about the partial derivative being able to indicate whether the z value, the dependent variable, was increasing or decreasing as that variable, x or y, was changing. So as x was increasing, going from 1 to 2 to 3, etc., was the z value going up or down, right? And the same with the y variable. And today, what we want to talk about, what we talked about at the end of class yesterday, is the slope of the tangent line. Now, I want to go back through this a little bit more carefully because this is something that we're going to use quite a bit in this class. So I want to make sure you understand it. The partial derivative of the function with respect to x turns out to be the slope of the trace of the function when you hold y constant and intersect that plane y equal b. So you've got this surface out here, and you're going to slice through the surface with a plane y equal b, and wherever it slices through that surface, it's going to create a trace, right? So we usually call those vertical traces. Now, when we're doing, of course, contour lines, that's where z is the constant, all right? So then we call it a level curve or a contour line. But when we're holding x or y constant, we call it a vertical trace. So we've got this vertical trace here, and it turns out that the partial derivative with respect to x is the slope of that trace at any point. So we just need to find a point on the trace where the y is being held constant, but the x is being allowed to vary. And this will give us the slope of that particular tangent line. And the same is true for the partial derivative with respect to y, except this time we're holding x constant. So we have the plane x equal a, and it's slicing through this plane x equal a. So you've got your surface here, and your plane x equal a is slicing through it like this. Okay, so when you have that, then you've got this trace again where the plane intersects the surface, and the partial derivative with respect to y is going to be the slope of the tangent line at any particular point. All right, so let's go ahead and go through this example. Now, this is one we've looked at before in a previous section. So we have this graph right here. Negative x squared minus y squared plus 2x plus 4y minus 1, which is basically a downward opening paraboloid. All right. So we have this downward opening paraboloid, and we know it's downward because these are both negative, right? So it's downward opening. And we want to look at the trace when we hold y constant and allow x to vary. So we're going to set y to be 3. Now, I have to tell you what constant value to use for the other variable. So this isn't something that you're supposed to, y3, I just picked it at random. So we're going to do it for y equal 3. Now, the function is solved for g as a function of x and y. But if y is going to be 3, we can replace the y here and here with the 3, and that will leave us an equation in just x. And since we have an equation in just x, we can let x be t, the parameter, and then we have x equal t, y equal 3. And then we replace y with 3 and x with t, and we get z as negative t squared plus 2t plus 2. And this is going to be, of course, the trace, right? So let's go ahead and look at this one. If I can get my thing working. Clonk, clonk, clonk. Takes a little while. Okay, so now we've got it right here. So the trace is this yellow line that you see right here, this downward opening parabola. And that plane right there, of course, is the plane when y equal 3. You can see that y equal 4 right there. And if I can get it to stop again, right there, you can see y equal 4. So this is probably y equal 3. All right. And where it intersects that downward opening parabola, we get this trace right here, this yellow downward opening parabola. That's the vertical trace. Now, the next thing we want to do, of course, is we want to figure out a tangent line at some point. So we're going to have to pick a point on that trace. Now, we know the y value is 3. But x is being allowed to vary, right? So x could be basically anything in the domain of G. So in this case, what we want to do is we want to find a point so that we can find the slope of the tangent line there. So we've got our equation right here in terms of just x. So I just randomly chose x equal 3. So once I know that x is 3 and y is 3, then I'm evaluating z at 3, 3. So 3, 3 is the point in the domain, the xy plane right here, and it gives a z value, which gives us a point on that paraboloid. And so when I plug it in, I end up with -1. So my value is 3, 3, -1. Now this is a point on the surface when x is 3 and y is 3. Because it's on the one where y is 3, it's also got to be on that trace. So here's the point right here. You can see it right there on that. And if we want to, we can come over here and we can plot our point. What did I say it was? 3, 3, -1, 3, 3, -1. And it's not showing up too well, so let's make it turquoise and we'll make it really big, size 8. So there you can see it right there. You can see that it's on the plane and it's on the trace and it's on the surface. So it's on all 3. And what we want to do is we want to find the tangent line at that point. Now the partial derivative with respect to x at that point should give me the slope of the tangent line. So I'm going to come back over here and we're going to find the partial derivative of the function evaluated at this point from the domain of 3, 3, or at the point 3, 3, -1. All right, 3, 3 is in the domain, 3, 3, -1 is the point on the surface. So here's my function g again, -x² minus y² plus 2x plus 4y minus 1. The partial derivative with respect to x would be -2x, that -y² would zero out, plus 2, and the plus 4y minus 1 would also zero out. So I have -2x plus 2, and so the only variable I've got is x, and I chose x to be 3, so I'm going to plug in 3 and I get -4. So this means that every time x goes up by 1 value, along this thing, z is decreasing by 4, all right? X goes up by 1, z goes down by 4 at that particular point, all right? So you can take another point on the tangent line if you wanted to, but you don't need to. So here's our tangent line right here, and I'm going to rotate it so that you can see it. All right. Now, one of the things that we need to be able to do is we need to be able to plot this in Calc3D. So we have to come up with a method of getting that line. Now, we know when we want to graph lines in 3-dimensional space, we have to use a space curve, so R of t. But we have x, y, and z, so we don't have a t. So we need to somehow convert this into a space curve so we can plot the tangent line. So what we do is we create a vector valued function, but not a function of t. I know that sounds kind of crazy, but we're going to create a vector valued function of x and y. Really, all we're doing is we're taking the equation for z, which is our g, and putting it here as the third component and letting x be the first component and y be the second component. So it's almost like writing the equation, but saying use x for that independent variable, y for that independent variable, and this is the function z that depends on x and y. So this is a vector valued function, but it doesn't depend on t, it depends on x and y. But that's a problem because Calc3D doesn't plot things as functions of x and y other than z, the scalar valued function. This isn't scalar valued anymore, it's a vector valued. But we can find the partial derivative of it. So we're going to find the partial derivative by taking this function, vector valued function of x and y, and taking the partial with respect to x. And as you would expect, you get 1, 0, negative 2x plus 2. I mean, this was the partial of z with respect to x. And of course, y is being held constant, so it zeroes out. And the partial derivative of x with respect to x is 1, like it always is. So we've got this right here. Now we know what our point is, 3, 3, negative 1. So if we take that and we plug it in here, we get 1, 0, negative 4 as a constant vector. Right? Now we already knew this because we already evaluated the partial derivative of g with respect to x at that point, and we got negative 4. So in essence, what we're getting is a vector in the direction of the tangent line. Now, how do we do a vector parameterization of a line? So a vector parameterization of a line requires a point and a vector in the direction of the line. And we have that. We have our point 3, 3, negative 1, and we have the vector in the direction of the tangent line. So what we do is we write it in the vector parameterization form, which is sort of parametric, and you'll see it down here, right? So let me get my cursor to show up for you guys. So you can see right here that what we have is we have the position vector for the point 3, 3, negative 1 added to t times the vector that's going along the tangent line. And if I combine these together, I know this sounds crazy, but if you combine them together, you get 3 plus t for the x component and 3 times 0. Why is that 3? That should be a 0. Oh, 3 plus 0t, my bad, that's 3. And negative 1 plus negative 4t for the z component. And this will plot the tangent line as a space curve. So we took it as a vector valued function of x and y. We took the partial derivative, we plugged in the point, we got a vector in the direction of the tangent line. Then we took the position vector of the point and the vector in the direction of the tangent line multiplied by the parameter t, added them together, and this gives us the vector parameterization of that line. And so when you graph it, you can see it right here. Okay, so somebody help me remember this. 3 plus t, 3, and negative 1 minus 4t. Okay, 3 plus t, 3. I'm never going to remember that. Okay. 3 plus t, 3, and was it negative 1 minus 4t? We'll find out. Aha. Okay, now it's probably not showing up real well, so I'm going to tell it to use a constant color. Blue is fine. And notice my t, you'll notice right here that we do have it coming down, but it's not going up, but that's because of the parameter t is only going between 0 and 2 pi. So let's make it negative 10 to 10. And if we want to, we can make that line darker or heavier. by increasing the width of it, maybe to 4 or 5, something like that. And now you can see it. Now you may say, okay, but that doesn't look like a slope of -4 to me. Well, because you're not looking at the XZ plane. In order to see the actual slope, you have to be looking at the plane. Remember, we held Y to be constant, so let's take Y out of the equation. You can use Alt Y on your graph, and that will plot it looking at the XZ plane, right? Now, does everybody see that this does have a slope of -4 when you plot it this way? Ours is actually a little bit on the back side of this thing, but that's basically where it is, okay? Are there any questions about that? You guys are being awfully quiet, so I'll open it up to questions. Do we have any questions? Still very quiet. Are you awake? This is the bad part about teaching to little black dots. Okay, yay, we have at least 2 people awake. Okay, all right, so that's an interpretation of the slope, the partial derivatives, as the slope of the tangent line to the trace when you hold one of the variables constant. Now, we looked at this one just a second ago in a different view, and now we want to look at it down here. Now, on this particular one, you'll see right here, this is the 2D image, right, that you've got going on right here. So when we're looking at this one, notice that it's in the XY plane, right? And notice that the tangent line, that's what this blue line is right here. The pink dot is, of course, our point, 3, 3, -1. And this red circle is the contour line at Z equal -1. So you can see up here, I set Z to be -1 and just ask for one contour line. So it's right here. And that line, believe it or not, is actually parallel to the x-axis. So the slope of that line is the partial derivative with respect to x, and it's parallel to the x-axis. So if you were going to take a partial derivative with respect to y, it would be parallel to the y-axis. Now, it really doesn't look like it is when you look at it over here. I mean, that doesn't really look parallel to the x-axis at all. The only way to kind of tell, and I should probably just do Alt X, is to, oops, and it moved. Of course it did. To get it so that the X is sort of zeroed out. So you're looking at the YZ axis. And again, you can do Alt X and that will zero it out. And then you can tell that the line is parallel to the x-axis. It's just hard to see it, right? Okay. You'd have to rotate it like this, and then you can see that it is definitely, okay, it went all wonky on me. If I could get it to stop in the right spot, it would be parallel to X. Okay, well, you can kind of see it right there. Finally. Okay, you can see that's more or less parallel. Now, in Calc3D, they are skewing the image a little bit so that it looks 3D. So things that should be parallel aren't always exactly parallel when we're talking about a 2D image, right? Now, what if we want to find the slope of a tangent line in a direction that is not parallel to the x-axis or the y-axis? Well, then we need what are called directional derivatives, which we'll be covering next week, all right? So when we have a directional derivative, then I don't have to go parallel to x or parallel to y. I can say, I want to go that way, or no, I want to go that way. I want to go in any direction I want. Then we need a directional derivative. And in order to do that, I'll need a vector in that direction, right? So I'll have to have a unit vector in that direction, which I can either use the angle theta to rotate me around in that direction, or there are other ways of getting it as well. Let's go ahead and take a look at example 6. So in example 6, we want to do exactly what we did in the previous work. we want to find the slopes of the traces to z equal 10 minus 4x squared minus y squared. Again, downward opening paraboloid, I believe, at the point where xy equals 1, 2. So 1, 2 is the point from the domain. It's the input value. And when we plug it into this function, we'll get an output, which is the z value. And then we want to write the equations of the tangent lines at that point in their vector parameterization form, right? So as a space curve. So first thing you should do, of course, is plug in 1, 2 to figure out what z is. You know what point you're dealing with. So when x is 1, I get 1 squared is 1. So this is 10 minus 4, which is 6. 2 squared is 4. So 6 minus 4 gives me 2. So this is the point 1, 2, 2, right? So here's the graph. It's a kind of a skinny little paraboloid, right? Skinnier in one direction than the other, right? It's an elliptical paraboloid where the contour lines are ellipses and not circles. So you can see the point right here, and we want to find the slope or the tangent lines to the two traces. There are two traces because there are two independent variables. So if we want to find the one where we hold y constant, we take the partial with respect to x. And that means that because our point is 1, 2, 2, then we're going to have to intersect that with the plane y equal 2. And that would be the partial with respect to x. If we want to do the partial with respect to y, then we'll hold x to be a constant. And so x will be 1, and we'll intersect it with the plane x equal 1. So here's what it looks like with those two planes. And I'll go ahead and open these guys up. Right, so when you're looking at this one right here, you can already see I've got the trace already put in there, and I've got the point as well. Right. Okay, now you know that this one has to be the partial with respect to y, because that plane is an x equal value, in this case x equal 1, all right, because that was our x coordinate. Right? So when we're looking at this one, remember how you go ahead and find the space curve to represent the intersection. You're holding, in this case, x constant to be a 1. And so since x is a constant 1, when you replace that in here, you get 10 minus 4, which is 6. You have 6 minus y squared. So if you have 6 minus y squared, you're going to let y be t, and then x is 1, and then z is 6 minus y or t squared. So let's look over here. So x is 1. Get my cursor to show up again. X is 1, y is t, and z is 6 minus t squared. Are there any questions about how to get that intersection? No questions? All right, I'm giving you time to put it in the chat or turn on your video or turn on your audio and ask. No? Okay. So once I have that, I want to know what the slope of the tangent line is so that I can find the equation of the tangent line. All right, now I need a point and I need a vector in the direction of the tangent line. I have the point, that's 1, 2, 2. I need a vector in that direction. And the way that I can do that is by letting this be written as a function of x and y as a vector valued function. So let's go ahead and represent that. I thought that I had done it. Where is it? Here we go. All right. So we need which one do we want to work on first? I guess we'll go with the one that we've been working on, which is where x is a constant. So we're looking at the partial with respect to y. So the partial, and I can't remember, partial, did I use f? I didn't use either, so we'll just say z. Okay, so the partial of z with respect to y is going to be, come back up here so you can see the equation. We've got 10 minus 4x squared minus y squared. So the 10 and minus 4x squared zero out, and I get minus 2y. Okay, so that's the derivative, holding everything constant but y. So I have minus 2y. Now I need to evaluate this at my point, which was 1, 2, I don't remember what the z component is, but z won't show up anyway. 1, 2, 2. All right, so now I'm going to evaluate partial of z with respect to y at the point 1, 2, or 1, 2, 2. You can write it either way. This is the point in the domain, or 1, 2, 2 is the full point on the surface. And this is going to give me a negative 4. That means the slope of the tangent line has to be negative 4. Now, the next thing we do, of course, is we represent the function as a vector valued function of x and y. So we just replace and we write x for the x coordinate, y for the y coordinate, and then we write the z value for the z coordinate, which is the function itself, which was 10, sorry, my computer keeps going to sleep, 10 minus 4x squared minus y squared. All right, so we have that. And then we're going to take the partial derivative with respect to y, because that's what we're looking at. We're holding x constant. So this one will zero out. We'll get 1 here, and we'll get minus 2y here. 0, 1, minus 2y. And then we plug in our value. Essentially, you should be able to almost do this without writing all this down, because you know the x is going to zero out, you know the y is going to be a 1, and you know that the derivative value, the partial derivative, is going to be whatever you got for the partial at that point. So evaluating at 1, 2, you essentially get 0, 1, negative 4. Now I have the two parts that I need. I have a point, which is 1, 2, 2. And I have a vector in the direction of the tangent line. So what I'm going to do is I'm going to take the point as a position vector, which is going to be 1, 2, 2. This is the position vector of the point. And I'm going to add to it t times 0, 1, negative 4. Now, I will take it written this way, but you can also combine it together, which would make it a little bit easier to put it into Calc3. So this would give me 1 plus 0t, 2 plus t for the middle component, and 2 minus 4t for the last component, right? So let's see, 1, 2 plus t, 2 minus 4t. One, 2 plus t. Uh-oh, I forgot the other one. 2 minus 4t. 2 minus x. I got a white keyboard thinking it would be cool, and you can't see the letters on the keys. It was the dumbest thing I've ever done. Okay, maybe not the dumbest thing I've ever done, but it was definitely dumb. All right, so let's use a constant primary color. Now we can see it right here. All right. So we've got our line right there. Oh, there we go. And it does look like it has slope of, what did we say, negative 4. Okay. Does that make sense to everybody how we did that? Okay, go ahead and take a few minutes and repeat the process yourselves at home on this one. And this one, of course, is where we're going to hold y constant, and we'll take the derivative with respect to x. So I want you to go through all the steps that I just went through. Okay. So again, there's my paraboloid, which actually it probably needs a little bit better resolution. So if I increase the number of grid lines to 60, that's better. Okay. And then I have my plane, y equal 2. And then the intersection comes if y is 2 and you plug it into this equation, you get 2 squared is 4. 10 minus 4 is 6. So you have 6 minus 4t squared. And x is t and y is 2. All right. Okay. So the next thing you need to do is take the partial with respect to x. All right, and let me scroll up so you can see the equation again. There it is. All right, so somebody turn on your microphone and tell me what the partial with respect to x is. Hello? Somebody turn on your microphone. I'm not hearing anybody. Or you can type it into the chat window if you can't figure out how to turn on your audio. What is the derivative of the function with respect to x? Maybe this will be a better viewpoint. Yes, Ian is correct, negative 8x. All right. So we have negative 8x. And then the next thing we want to do is we want to plug in our point, which is 1, 2, 2, or 1, 2 from the domain, which would give me negative 8. So the slope of the tangent line at that point, holding y constant, is going to be negative 8. Right? Now we can go through these steps again. So again, we've got r as a function of x and y, but this time we want to find the derivative with respect to x. Holding y constants, you know that's going to give you 1, 0. And then the derivative with respect to x would be our negative 8x. Oops, lost my x. And when we plug in that value, we know that we get negative 8. So this is our vector in the direction of the tangent line. We have the same point that we had before. So our point is still 1, 2, 2. So we're going to use this vector and that point in this format, and this will give us the tangent line for that part. Okay. So we're still using the same point. So somebody type it into the chat window or turn on your mic and tell me what my space curve is. What do you get? What's the first component in the I hat direction? I've heard from Ian. I'm going to start calling on people.
It should be 1 plus 1t.
1 plus t. Thanks, Jay. What's the next part?
0. Oh no, 2. It should just be 2.
2
Sorry.
plus 0. Yep. And the last part?
2 minus 8t.
2 minus 8t. I'm never going to remember that. 1 plus t2. 2 minus 8t. All right, use a constant color. Make sure that your t value is going in a normal range, -10 to 10. It's not trig based, so we don't need -2 pi to 2 pi. And you can see it right there, right? Now, again, we did this where we're holding y constant. So to check that the slope is really a -8, we need to take y out of it and look at the xz plane. So hold down the Alt key and hit Y, and it will give it to you. It's kind of hard to see. It's right here. If I made it thicker, it would show up. And also, if I make my curve, my surface transparent, it will show up better. And my line, I'm going to make it a 5 in width. Right? And now I can see it. And yeah, it is. It's very, very steep and sloped in the negative direction. Are there any questions about that? No? Hey, if I asked you on this one, which one you had to take the derivative with respect to, what would you say? Based on the contour plot right here, and the fact that it's parallel to the x-axis, which derivative did I take the partial with respect to? X or Y?
Y.
X.
Okay.
It's weird, but it's parallel to the one you took the partial with respect to. So
Okay.
this one would be the partial with respect to X, right? The one we just did, right? And this one would be the partial with respect to Y, the first one we did. Okay. All right. View 3, looking at partial derivatives from a contour map. This is a lot less important, so I'm going to go through it relatively quickly. It's not really a practical way to do things, but it can be done this way, and I think there is maybe one homework problem that covers it, so we'll do this a little bit. Okay, so on example 7, instead of looking at the surface, we're looking at the contour plot, right? So all the level curves. And we want to approximate the partial derivative with respect to y at the 0.35. Now, a partial derivative with respect to y, we're holding x constant. So this is the intersection of the surface with the plane x equal 3, all right? And this is the contour diagram that we have to work with right down here. So when we're looking at this one, what do you suppose you're going to do, right? What would be your first steps when you're looking at this guy right here? All right, so we know we're holding x constant. Write that down. It's the intersection of the surface with the plane x equal 3, because it's the partial with respect to y. So x is called constant. The problem is I don't have the surface, do I? I have no information about the line at all. So we have to go back to sort of the definition of what the partial derivative is. And what is the partial derivative? By definition, what is the definition of a derivative, period?
Limit.
It's a limit of the difference quotient. So we're going to go back to the difference quotient. We're going to use that to approximate. So we can approximate the partial derivative of this function with respect to y by finding f of x naught, y naught plus h. Remember, y is changing, but x is constant, minus f of x naught, all divided by h, right? So we're just going to approximate. So if I'm doing this one, I need to figure out, okay, I'm going to hold these things at, oops, I forgot my why not. I'm going to hold x constant and I'm going to vary my y. Right? So looking at the plot right here, if you're looking at the plot, we're going to hold x to be a constant and we're going to change our y value. And we're holding x to be constant at 3. So down here along the horizontal axis, locate x equal 3, which looks like it's right here in between the second and third curves at the bottom. And then we want to find 2 y values. So we want to try to find points where it looks like it's cutting through pretty close to exactly, all right? There's not perfect, but I would say that f of 3, 5,
3, 5.
about
3, 3, 3, and 3, 5.
yeah, and f of 7 would be about 16. All right, so I'm holding x constant at 3, and I'm looking at f of 3, 5, which is about 14. And then I'm looking at another point, still holding x constant at 3, but at 7, it's about, what did I say, 16? Okay, so these are my values. Again, I'm trying to evaluate at 3, 5, so I have to choose 3, 5 for one of them. But the other one is arbitrary. I could have gone up or down, it doesn't matter. But it looks to me like this is kind of what I've got. How much did I change my y value by? I went from 5 to 7, so my h must be what number?
2.
2, okay. So then my partial derivative with respect to y is going to be approximately 16 minus 14 divided by 2, which is 2 over 2, which is 1. So the slope of the tangent line at that point has to be 1 or approximately 1, because this is an approximation. Right? Any questions about that? It's kind of a short one. Short and sweet. All right. And then I have the directions down there if you want that. Okay. Let's look at another one. This one, we're using the contour map to approximate the partial derivative. This time we do have the surface, which is a downward opening parabola at the point 1, 2. I think we've already done this once. All right, so if we're looking at this one right here, how would we use the contour plot to do that? Well, we'd have to produce a couple of different contour lines. And so the first one I did was I took the contour line at c equal 2, because when x is 1 and y is 2, then z is 2. And I wanted to evaluate at the point in the domain 1, 2, and that would give me a z value of 2. So I have to use 1, 2, 2. That's my target point. Now the other point is arbitrary, but I don't want to get too far away. So for the first try, I chose to use x equal 1.5. Now remember, we're doing the partial with respect to x, so we're holding y constant. So y is going to stay 2 for the duration. And now we can evaluate that, and we can plug in into our equation. Y is 2 and x is about 1.5. That's what we're using for our approximation. When you plug it into the function, you get a value of -3. All right, so that's your target value for where you are, and that's scooched over a little bit. So this is my f of x naught plus h y naught, right? And this value that we got up here is my f of x naught y naught. That's my target point right there, right? So then I take the difference between the two values, 2 minus a -3, and then I subtract the x coordinates. I had 1 minus 3 halves, and I end up with about a -10. But I believe when we did this, we got a slope of -8. So this isn't all that exact, right? what's the problem? Why is this so far off? It's not horrible, but it's definitely not that close. Why is it so far off?
Well, because you're half a point away, so we're just doing the secant line.
Yeah, I'm really getting the slope of the secant line, and 1.5 isn't all that close to 2. If you're wanting the tangent line, 1.5 isn't that close. So let's do it again, but this time let's choose something that's a lot closer. So this time we're going to choose x to be 1.01, right? So our h is going to be 0.01 instead of, what was it the first time? A half. So instead of being a half, it's going to be 0.01. The y is still 2 because we're doing the partial with respect to x. So we still have -4 here, but now we're squaring 1.01. We come up with this z value. And this z value is going to be our f of x naught plus h, y naught. And then we evaluate again with what we got at 1, 2, which was the number 2. And this time you get negative 8.04, which is pretty darn close. All right, the true value is negative 8, which we proved previously. But this is again just doing an approximation. All right, so you can use the contour lines to do it, right? Or the contour line concept. All right, are there any questions on anything so far? Not, I'll keep plowing ahead. Okay. All right, this is just a real short, just to make sure that you're aware. Partial derivatives of functions of more than 2 variables, the definitions are going to be very similar to what we had before. And we talked about this yesterday in class. The partial with respect to x, you're changing x from just x to x plus h, but y and z stay constant. If you're going to do the partial with respect to y, then the value of y goes from y to y plus h, but x and z are held constant. And if you're going to do the partial with respect to z, then you hold x and y constant, and z changes from z to z plus h. And when you take the derivative practically, you do exactly the same thing, right? You hold the other 2 constant and allow the third to change. So go ahead and take a couple of minutes and figure this one out. And then I'll call on somebody to give me the solutions. Okay, I'm going to warn you in advance. Jacob, I'm going to call on you for the partial of f with respect to x. Kyrie, I'm going to call on you for the partial of f with respect to y. And Max, I'm going to call for you for the partial of f with respect to z. So you can either type it into the chat window or you can turn on your mic and let me know when you've got it done. So Jacob for the first one, Kyrie for the second one, and Max for the third one. Jacob, are you ready? Jacob has gone to the bathroom. Yeah, you know that I'm going to call on you in class when we're doing it remotely because I got to make sure you're not snoozing.
I'm sorry, is that me?
Jacob.
I thought there
no,
was a
not
Jacob in class.
Jacob.
I'm Jake. I've never been Jacob.
Yep, yep. No, I've got a Jake and a Jacob. Jacob, are
Okay.
you there? Actually, I think he dropped. Okay, Jake, go ahead and let me know.
So we're doing partial with respect to x.
Yep,
So it's secant x squared y, tangent x squared y. Is that times x squared?
not times x squared. What would it be multiplied by? Take the derivative of the inside function with respect to
So
x.
x squared times x squared, which would be x
No,
to the
no,
fourth.
no, careful.
No,
Derivative
because I'm only taking a derivative of x squared y once.
once.
X squared is a, I'm sorry. So is x squared here a constant?
No, y
Y
is
is
a
the constant.
constant.
Okay,
You're
that's my
doing the
problem.
partial with respect to x. So what would it be?
Just times y then, or
2xy.
2xy.
Yep, remember, take the power to the front, reduce the power by 1, and then multiply by what's left,
Okay.
right? So you have 2xy, secant of x squared y, tangent of x squared y. And then what about the second part?
I'm sorry, where's the rest of the,
The tangent of x cubed yz squared. So what's the derivative of tangent?
so secant squared
Yep, so
of
secant
the x squared
squared,
y,
and we'll leave the inside alone, x cubed
x cubed
yz squared.
squared.
Now the yz squared is just a constant. So how do you take the derivative of x cubed?
So leave the yz squared and then multiply by 3,
X,
3x.
3x squared.
3x squared, yeah, sorry.
Yep. So 3x squared, yz squared. Yep. Questions about that one? Does that make sense to everybody? Okay. I'll share my screen with you again. You can see it. Okay. All right. What about the next one? Kyrie, can you take the next one?
Yeah, it's gonna be x squared, secant of x squared y, tangent of x squared y,
Okay, so secant x
minus,
squared y, tangent x squared y
times x
times
squared,
times x squared, which we usually put at the front. Then what?
minus secant squared x cubed y z squared
Yep,
times x cubed z squared.
excellent. All right, and then I said max for the last one. Are you ready, Max?
Yeah. Would it be negative 2x cubed yz secant squared of x cubed yz squared?
Okay, say that a little slower. Negative 2x cubed
Yz
yz.
secant squared with x cubed yz squared.
Yep, that's it. Okay. Does that make sense to everybody?
Yeah,
You're
for some
holding-
reason, when I did mine, I did x squared. So I did respect to y. That was my first thing instead of respect to
Okay.
x.
Yeah.
Yeah, because I had x
When you're
squared, secant
holding-
x squared y, yeah.
Yeah, when you're
I just
going
had
with
those
respect
backwards.
to x, hold y and z as constants. Only the one that's mentioned is a variable. Okay. Now, can you do higher order partial derivatives? Yes, you can. You can do second derivatives, third derivatives, fourth derivatives, but it gets a lot more complicated because you now have more than one independent variable. So you have to say which one you're doing the derivative with respect to first, and which one you're doing the derivative with respect to second. And if you're doing a third derivative, which one you're doing the derivative with respect to the third time. Now, there are some times when the order doesn't matter. We'll find out why in just a minute. or when that happens. But there are occasions where the order does matter, and the partial derivative with respect to y first and then with respect to x is not the same as the partial with respect to x and then with respect to y. So we're going to have to be very careful about when we do our partials as to which one we've got. And in this case, we cannot, again, use prime notation because we have to say which order we're doing the derivatives in and which one we're doing, all right? So this is the partials, the possible partials that you can have for a function of two independent variables, x and y. And you can see different ways of writing it. You'll see that we do use that 2 in the power position notation if we're using the partial with respect to the same variable 2 times in a row. So this means the partial of x first, then take the partial with respect to x again, all right? So just like in normal order of operations, you do what's in the parentheses first. So this is the partial of f with respect to x first time, then do the partial with respect to x again. And you have the same notation for the partial with respect to y both times. However, over here, this is where it gets confusing. Which of these went first? When you're looking at this third one, was it the partial with respect to x or the partial with respect to y? Well, it actually is backwards. This is one of the few times in mathematics that we go right to left, not left to right. And that's because there are understood parentheses here where the partial was done with respect to y first, even though it's written second. And then we did the partial with respect to x. So you have to interpret this one as the partial with respect to x after you've done the partial with respect to y. That's the way of thinking of it, which is not necessarily the same thing as the partial with respect to y after you've done the partial with respect to x, right? Those aren't necessarily the same thing. Now, there's another notation that we use a lot because we're mathematicians and we're lazy. We don't like to write things down. And then we write the partial with respect to y and x, and the partial with respect to x and y. Now, you would think that when they did these, they would have chosen the order to do the same thing as the fractional notation, which is in reverse order, right to left, but they did not. These go left to right. So if this says the partial of y, x, then you're actually doing the partial with respect to y first, and then the partial with respect to x second. And if it says the partial with respect to x, y, you do the partial with respect to x first, and then the partial with respect to y second. Now, we're going to talk about when these turn out to be the same thing in just a minute. For us, most of the time, they are going to be the same thing. It has to do with continuity. If both the partial with respect to yx and the partial with respect to xy, if both of those are continuous functions, then they turn out to be identical. They're actually equal to each other. It's called Clause's theorem. And it turns out that it depends on continuity. So again, continuity, even though we don't actually prove that things are continuous very often, continuity is a huge topic and very important because it's a condition for many of the theorems we want to use. So let's go ahead and practice this one. Let's calculate all 4 second derivatives of this function. So when we're looking at this one, we're going to do all right, so I'm going to do the partial of f, and I'll write the 2, indicating I do the derivative twice. And I'm going to do it with respect to x both times. So this is the partial with respect to x of the partial with respect to x. So this means that I'm going to do the partial again after I've done it once. So the first time I do it, the derivative of sine is, of course, cosine. and I freeze the inside, 3x minus 2y. And then I multiply by the derivative of the inside with respect to x, which is 3. Probably didn't need that much space. Then the second one, the derivative of cosine is negative sine. And this stays x plus 4y. And then I multiply by the derivative of the inside with respect to x, which is 1, so I can just leave it. And I have this expression here. Now I need to do the derivative again with respect to x. So this time the derivative of cosine is negative sine. So I've got a negative sine 3x minus 2y, but I get another 3 popping out. So I actually have negative 9. And on the second part, derivative of sine is cosine. And again, the derivative of the inside is 1. So this is what we have for the first one. Are there any questions about this one? Does that make sense to everybody? Okay, running out of time. Okay, let me do the partial with respect to y both times. And I think probably I'm going to need a little bit of space. All right. So weird. I didn't want to copy. All right. Okay, so there's my thing. And the partial here is going to be cosine of 3x minus 2y times a negative 2. And again, I have to do the partial with respect to y again. And then I'm going to have minus sine of x plus 4y times 4. Then when I do it again, I get still negative, no, positive now. Cosine's negative sine. So I have sine 3x minus 2y. And I get another negative 2, which would make it a negative 4, I think. Let me check, double check. Yes. And then on the second part, I've got the sign is going to probably stay the same, so negative. And I've got cosine of x plus 4y. And I've got another 4 coming out, so that's going to give me 16. All right. Now, what I want you to do is I want you to go home and I want you to do the partial derivative with respect to x first and then y, and then compute the partial with respect to y and then x, and see if they're the same. All right. So hopefully we'll be back in the classroom tomorrow. I expect we probably will be. They'll get the roads at least cleared enough for us to be able to drive. So I will see you guys tomorrow, and we'll pick up with this tomorrow. We'll finish it up, and then we'll look at tangent planes and linear approximations. So if you have any questions, you can hang out and ask. Otherwise, I will see you guys tomorrow.